As we look at chapter 7, we are going to be starting out looking at exponential functions. More specifically, today we're going to be looking at exponential growth. But we're going to be looking at exponential functions. Now, as I look at an exponential function, I notice what word is actually contained in there. Exponent. Exponent. Right inside of exponential, we have that word exponent. And what you want to think about an exponential function is that x, my variable, x, is in the exponent. So, it will always have the form y is equal to a times b to the x. Now, my a can't be 0 or I've created all sorts of problems for myself. It just is going to completely eliminate the whole thing. Y is equal to a times b to the x. Now, we are specifically looking today at exponential growth functions, and in an exponential growth function, my b value, the base, has to be bigger than 1. Another way that we refer to that b value is when it is an exponential growth function, we actually call it the growth factor. My b value is what we refer to as the growth factor. That base, when we're in exponential growth, has to be bigger than 1. All right, now, a couple of things have to happen. There are some very easy and nice points to think about on our graph. If I put 0 in for x, does anybody have a suggestion on what my value for y will be? If I put 0 in for x, y is equal to a times b to the x, what will I get for my y? A. Very nice. Fantastic. If I put 0 in for x, anything to the 0 is 1, so I multiply by a, and at 0 I will always be at a. At 0, I will always be at a. Now, where will I be at 1? Where will I be at 1? A times b, because b to the first is going to be b, so it'll be a times b. So at 1, I'm going to be somewhere up here at a times b. Now, exponential growth, when we have x in the exponent, my graph will always look like this. It is not a line, it is a curve. It's going to curve up and to the right for exponential growth. And then it's going to come down and to the left for exponential growth, getting closer and closer to the x-axis. But my x-axis is a boundary for this graph. My graph is going to get closer and closer and closer to this x-axis, but it will never touch the x-axis. That x-axis is what we refer to as an asymptote. Very nice. A horizontal asymptote. Remember from before that an asymptote is a line that the graph approaches but never, ever, ever touches. A line that my graph gets closer and closer and closer to, but never actually touches. Now, x-axis, what's another way to describe that? Y equals 0. Very nice. The equation of the line for the x-axis is y equals 0, and that's going to become important in a little while. So I just want to make sure that we add that in there right now. Okay, our parent function. Our parent function is going to look like y equals a times b to the x. Now, we have graphed many functions. We have graphed many functions that have had this a value in them. Can somebody raise their hand and describe to me what effect that a value will have on this graph? Yep, Ben? All right. When does it open up? When it's positive. So if my a is negative, it opens down. Okay. So my a value, if the a is less than 0, if the a is negative, there will be a reflection over that x-axis, over that line of y equals 0. Perfect. What else does the a do? Anybody else have a thought on what the a does? Beautiful. Very nice, Kennedy. Stretches it or shrinks it. There is a vertical stretch or shrink. That A value tells me how tall or how short my graph is going to be. How tall or how short that graph is going to be. How fast it gets taller or how fast it gets shorter. Okay, now on my parent function, where is my y-intercept? Beautiful. Thank you, Justin. My y-intercept is at A. It crosses the y-axis at A for my parent function. And then it's always easy to graph that other point because for my parent function, I realize that when I plug in 1, my y value is going to be the A times the B. My y value is going to be A times the B. So these are all things that are true with my parent function. All right, what about my domain? Does anybody have a thought about my domain? Brianna, do you have any thought about what I can have for my x's? I can put anything in there for x I want. Absolutely. All real numbers. How about my range? Beautiful. Notice that this graph is above that x-axis. Notice that that graph is above that line at y equals 0. So my y values in this situation, when it's above that x-axis, my range is going to be y is greater than 0. Does anybody have any questions, comments, concerns up to this point? All right, let's try B down at the bottom. Let's try B down there at the bottom. Y is equal to the opposite of 7/2 to the x power. Now, just a comment, I like, first of all, to write down that parent function. I like to write down that parent function above it. Y is equal to A times B to the x power. Y is equal to A times B to the x power. All right, Marissa, what is my value for A? What? Beautiful. It's a tricky one, and that's specifically why I asked to make sure that everybody sees that. Notice that negative is in front of the parentheses. That negative is really what number? -1. So my A value is a -1. And what is my B value, Lena? 7/2, 7/2. Beautiful. My A value is -1. My B value is 7/2. I could have just as easily written y is equal to -1 parentheses 7/2 to the x instead of just that negative being out in front. Sometimes that can be tricky for us. All right. Knowing that that's our equation, Carly, can you give me one point that I can graph? Okay. What's the easiest point to plug in? 0. All right, so let's say we get to this point and we don't have any idea what this graph looks like. What do I get when I plug in 0 for x? All right, anything to the zeros, 1 times -1 is -1. Remember that my point for my parent function is at 0a, but if I forget that, it doesn't really matter. I can always plug in 0 for x and find out what my y value is. So I'm here at 0, -1. What is another point on this graph, Dennis? All right, 1a times b, so -1 times 7/2 is going to be -7/2. Once again, I forget, all is not lost. I plug in 1, well, 7/2 to the first is 7/2, times -1 is -7/2. So I go to the right one and down 3.5. Now, I could plot other points. I could make other points, but I should realize that I know what this graph is going to look like. Now, I'm a little bit confused, though. Why is it below the x-axis at this point? My A was negative, so my whole graph's going to be below that x-axis. Absolutely. So, my curve is going to go down and to the right here, and then it's going to go up and to the left, but it's never going to touch what? It's never going to touch that x-axis. Make sure that yours do not touch that x-axis in any way, shape, or form. Because that x-axis acts as what, Brooklyn? The asymptote, absolutely. I have an asymptote. I'm going to draw that as a dashed line. It is a guide for my graph, but it is not part of my graph. That's why we make it a dashed line. It's a guide for my graph. I know my graph gets closer and closer and closer to that, but it never touches that. So I make it a dashed line because it approaches it but never touches it. Okay, so looking at this, Ben M, what's my y-intercept? -1, absolutely. It crosses the y-axis at -1. All right, what's my asymptote, Marissa? And what is another way to write that? What's 0? Y equals 0, right? Horizontal line is going to be y equals a number, so my asymptote is y equals 0. All right, Jacob, what's my domain? All reals. And Maddie, what is my range on this graph? Okay, I like the y. Beautiful. Notice that this graph, because it's a reflection, it's below that line at y equals 0. So if my graph is below 0, it's going to be y is less than 0. Just something you got to tune in on so we don't make a careless error. Questions with that? All right, then. Yes, sir. You can graph 2 points because we know it's going to be that curve. You're exactly right. Yep. 2 points to make a line. I know it's 3 points to make a parabola, but I know what this curve looks like. I could make more if I wanted, but because we know the shape of the graph, we can condense that. Fair enough? No one's going to complain that I'm saving you work? All right. Then, taking a look at the next page here, we should realize, very quickly, we should realize that as we look at this, y is equal to a times b to the x minus h plus k, we should know we have made enough graphs. Hunter, what does that h do to my graph? Absolutely. The h is the horizontal shift. It shifts it left or right. Now, I want to point out something. I want to make sure everybody's aware, but I'm sure you already noticed that. Notice it's x minus h. It once again is the opposite of what is with that x. The patterns continue. The patterns continue. X minus h. It's the opposite of what is with my x for that shift left and right. All right. What does the k do, Heather? Beautiful. It is a shift up or down. Notice it is still positive k, so it is exactly as it looks. Math is about patterns, identifying those patterns. All right, so let's take a look here at example 2. Graphing y is equal to 2 times 4 raised to the x plus 2 plus 1. Now, I'm going to be very picky about this. I want more than one graph. I want you to start out with your parent function. I want you to start out with your parent function. Remember, as we've looked at other function families, our parent function is always everything through the x. So in this case, can somebody tell me what my parent function is going to be? Beautiful. Y is equal to 2 times 4 to the x power. Y is equal to 2 times 4 to the x power. Becky, can you give me one point that would be easy to graph on my parent function? 0, 2. I love it. It's at 0a. If I put 0 in here, 4 to the 0 is 1 times 2 is 2. So 0, 2. I'm going to put this on my graph here at 0, 2. All right, give me another point that would be easy to graph, Chelsea. 1, 8. Beautiful. 4 to the first is 4. 2 times 4 is 8. It's always at 1 and then a times b. So 1, 8. So I go to the right one and up 8. Now, I know what else about this graph, Marcus. Okay, even before that, I don't have my parent function on here. What else do I know about the parent function? It is exponential growth. So what is this going to look like? It's going to curve up and to the right. I like that. And down and to the left. All right. So it's going to go down and to the left, getting closer and closer to that x-axis because my x-axis is the asymptote. I'm going to put that in as a dashed line. It's a guide to my graph, and it's not part of my graph. All right. Now, there's my parent function. I put it on my graph. Kennedy, what am I going to do with that parent function now? Beautiful. Okay, I'm going to stop you for 1 second. That x plus 2, we know it's the opposite of what's with x. So the x plus 2 is going to force it to go left 2. And I didn't mean to interrupt you. I'm sorry.
And then up 1.
And my k value is a positive 1. So it's going to go up 1. Now, this is just a preference. It's not the way you have to do it, but I always like to move my guides to my graph first. I always like to move my asymptotes first because it just seems like my graph ends up looking nicer in the end. Now, if I move that asymptote left 2 and up 1, where does it go? Yeah, left 2 doesn't affect a horizontal line. So if I go left 2 and then I go up 1, my asymptote's right there at this point. Now, each point on that graph is going to go left 2 up 1, left 2 up 1, and then I'm ready to graph that curve down and to the left. Now it is getting closer and closer and closer to what? Line y equals 1. Absolutely. Okay, so y-intercept. Does somebody have a thought about the y-intercept in this situation? Where does this graph cross the y-axis? 17, 26, 39. Okay, let's think about what we know from Algebra 1. What do we always know about the y-intercept? X is always 0, okay? So my y-intercept, I always know that the x is 0. So if I come over here to find my y-intercept, well, I know that y is equal to 2 times 4 to the x, which is 0 plus 2, and then plus 1. So y is equal to, all right, 0 and 2 is 2. All right, folks, what's 4 squared? Times 2, add 1. So I know that this crosses the y-axis at 33. Do I see it on my graph? Nope, but I know that that's where it would cross if I continued my graph. All right, let's see here. Brooklyn, what is my domain? Beautiful. Every exponential function always has a domain of all real numbers. What is my range, Aaron? Beautiful. My graph is above that line at 1, so my range is going to be y is greater than 1. Fantastic. Any questions with that? All right. Now, where do we use this in the real world? Exponential functions are used everywhere. When we are changing by percents, when things are increasing or decreasing by percents, this lends itself to exponential functions. So, as we're looking at this situation, and we're going to be studying and focusing today on exponential growth, an exponential growth model, when a real life quantity increases. Today we're talking about increases by a percent. When it changes by a percent, it's going to be exponential functions. When it goes up, it's exponential growth. Increases by a percent each year. The amount y of the quantity after t years is modeled by, here's my equation. You need to know this equation, commit it to memory. Y is equal to A times the quantity of 1 plus R all raised to the t power. This is actually an equation you should have seen in Algebra 1. This is an equation you should have seen in Algebra 1. Y is equal to A times the quantity of 1 plus R all to the t power. All right, what do those pieces mean? Here we go. A is the initial amount. The A is the starting amount. How much you start with at the beginning. All right. The R is the percent increase. The percent increase. Now I got a question for you. How do we write percents? As decimals. Okay, so we're going to change it to a decimal. And then T is usually time, and yes, I heard it, in years. All right, so how are we going to apply this? All right, 1970, the population of Kern County, California, where Bakersfield is located, was about 330,000 people. 1970 to 2000, the population grew at an average annual rate of about 2.4%. All right, let's say I don't know anything about this situation, but the minute I get to the end of this, I get pretty excited. I see that it grew at a rate of 2.4%. The end. I'm excited. It grew at a rate of 2.4%. It is increasing by a percent. I see that it's going up by a percent. When it goes up by a percent, I should know that's exponential growth. When it's going up by a percent, that should tune me in to exponential growth. All right, so let's look at this situation. Write an exponential growth model giving the population P of Kern County at T years after 1970. All right, we're going to quit right there. We're not even going to answer their question. The first part of their problem said write an exponential growth model giving the population P of Kern County T years after 1970. All right, so the population is equal to, all right, I'm going to use that equation, A parentheses 1 plus R to the T power. So P is equal to, are there any pieces that I can fit in there? Where is it going, Justin? A. My A value, it starts at 330,000. All right, any other pieces I can fit in there? The rate, what is the rate? Beautiful, 2.4%. I'm going to write it as a decimal, so that is going to be 0.024. And do I know the T? Okay, careful. Is it always 30? No, it can be anywhere up to 30, right? So we're going to call it T for time. So P is equal to 330,000 times 1 plus 0.024 is going to be 1.024 to the T power. Now, give me 1 second. When they ask me to write a model, this is exactly what they're looking for. A model is an equation. A model can be represented by an equation. You're writing the equation for the situation. Yes, sir?
What does the 1 do?
Think about a percent. The 1 represents what I have now. In other words, if I have the population is 330,000 now, that's 100%. So when I increase it, if it goes up by 2.4%, next year I'm going to have 102.4% of what I have this year, right? So I always have to add 1 to include what I had the year before. Does that make sense? So it's a little difficult to understand, to explain. Is that okay? All right. Now, let's say about how many people lived in that Kern County in 1990. What are we going to do to figure out how many people lived in Kern County in 1990? We could graph it. We could graph it. Graphing is just so yucky. Then we got to trace. Is there an easier way to figure out how many people there were in 1990, Brooklyn? All right. 1990 means it was 20 years later. So, P is equal to 330,000 times 1.024 to the 20th power. About how many people were there in Kern County? Raise your hand. Does somebody have that? Jacob, do you have that? How many people were living there in 1990? About 530,289 people. Sounds good. Now, they want us to make the graph. These numbers are ugly. This is going to have big, nasty, ugly numbers. We are going to incorporate our technology. So, grab your machine. Grab your machine. This is an appropriate way to use our technology when our numbers are big and messy. All right, turn it on, clear out what's ever in there. All right, going into y equals. Clearing out what's ever in there. I got lots of messy stuff in there right now. All right, so under y equals, I want to put this equation. The equation is 330,000 times 1.024 raised to the power of, we don't have a t, we have an x. All right, now, want to look at this graph, want to make sure everybody's looks nice and the same. So let's go to zoom. Zoom, and number 6 for standard. Zoom and number 6 for our normal graph. What happened? Why isn't it there? It only went to 10. Well, isn't that okay? Is that okay? Obviously not. I didn't get a picture, but why is that not okay? Yeah, what is my y-intercept of this graph? 330,000 is my A value. That's going to be my y-intercept. That's not going to be in here, is it? All right, so let's go to window. We got to go to window and we've got to make some choices based on this problem. Now, what is X talking about in this situation? Years. All right, what are we going to start it at? 0. What are we going to end it at? All right, why did you choose 30, Ben? All right, 1970 to 2000 is 30 years, correct? Let's pick 35 just to make sure that we have a nice looking picture. All right, I'm going to go by 5 so that there aren't too many tick marks on my screen. And then I need to think through this. What is my y representing in this problem, Tara? Okay, that's all right. What is y? Can somebody help? What is y representing, Aaron?
Yes. The number of people.
Okay. Number of people, right? Y is equal to 330,000 times 1.024 to the t. We found the number of people when we put in 20 for x. Now, where do I want to start my y's? 0. Any thoughts on how big I want my y's to go? What? 400,000. Why 400,000? I'm not saying you're wrong, but why 400,000? Okay, my minimum number of people is 330,000, so you're just going bigger than that. Now I got a question. At 20 years, how many people were there? 530,000. Do I want to quit at 400,000? No. What are you thinking, Lena?
I just have a question.
Yes.
How come we're not starting at 330,000 or like around there? Because like, isn't there? Then that's how it like it begins.
Okay. All right. All right. Do I have to start my y's at 0? Where do the y's start according to this equation? 330,000. So what are you thinking we should start at? 300,000, just to make sure we get a nice picture? I can live with that. Perfect. I have no problem with that. How big do we want my y's to go? 1 million. All right. All right. Might be too big, might not be. Let's go by then 100,000 on the y-axis. Let's see what we got on our graph. Now, when I look at this, I'm a little surprised. Is anybody else? You're okay with how this looks? I thought it was supposed to be a curve. Okay, but it's not it's very subtle, right? I mean, typically our graph look like this, right? But we only have one tiny little chunk, so we can see that it's curving, but very subtly. Does that make sense? Okay, so on my graph, I'm going to do the best I can. Okay, so my x's went from 0 to 35 by 5s. My y's went from 300,000 up to 1 million by 100,000. That's about the best I can do. And then I'm going to simply make a sketch. It's not going to be perfect, folks. It looks something maybe like this. Mine's probably not even very good at all. It's a little too curvy. All right, so there's my graph. I did the best I could using my technology. Now, my last question says use that graph to estimate the year when the population of Kern County is 400,000. Now, if I want to know when the population is 400,000, which variable do I want to represent? My y is going to be 400,000, right? So, let's go back into y equals. But now I want to know when is the y equal to... Oopsie. When is my y equal to 400,000? So I'm going to put a second equation in. I want to know when the y is equal to 400,000. Hit graph. All right, it's pretty exciting. I'm pretty sure it happens right here. How do I find that? Trace? Second trace. Second trace brings up a menu called calculate. What is it I'm trying to calculate? Where they intersect. So I'm going to choose 5. First curve, hit enter. Second curve, hit enter. And guess, hit enter. Enter. Nope. Enter, enter, enter. 3 enters. And what do you get? All right. So it's about 8.1 years. So when does that happen? About 1978, maybe January or February, 1/10 of a year? Somewhere way at the beginning of 1978. Questions with that? All right, one more situation. All right, talking about compound interest. Talking about compound interest. Everybody loves money. All right, dealing with compound interest. Another formula you need to know, commit it to memory. A is equal to P, parentheses 1 plus R over N to the NT power. A is equal to P parentheses 1 plus R over N raised to the NT power. Okay, what do these mean? My P is what we call the principal. If you're taking money to a bank, the principal is the amount of money you start with. The principal is the amount of money that you take out for a loan, or the principal is the amount of money that you put into your savings account at the beginning. The R is the annual rate. The interest rate, the annual rate. Now we know it needs to be a what? How are they going to give it to us? Percent. How do we need to use it? As a decimal. All right. Then N is a little bit interesting. The N is the number of times the money is compounded per year. The N is how many times the bank is going to do something with my money. So if it is compounded yearly, how many times is the bank actually going to do something with my money? Once. If my interest is compounded monthly, how many times is my bank going to do something with my money? 12. If they say quarterly, how many times is the bank going to do something with my money in a year? 4 times a year. What if they say semi-annually? Nope. Yep, it's a semi-annually is a half a year, so it's twice a year that they're going to do something with my money. What about daily? 365 times they're going to do something with my money. All right, so keep that in mind as we take a look at this situation. You deposit $5,500 in an account that pays 3.6% annual interest. Find the balance after 2 years if the interest is compounded with a given frequency, and we're going to talk about semi-annually. Okay, so we're compounding interest. So we know we're going to use the equation A is equal to P, parentheses 1 plus R over N to the NT power. Yes, sir. Yes. Yep, principal is the amount you start with. So A is equal to, what is the principal? How much money did I start with in this situation? 5,500. Parentheses 1 plus, what is R? Beautiful, 3.6%. We're going to write it as 0.036 over N. All right, what is my N going to be in this situation, Dan? 2. Semi-annually means the bank is going to do something with my money twice a year. All raised to the N once again is 2 times, how much time is going on here, Ben K? 2 years. All right, now it becomes PEMDAS. Now it becomes a situation where we need to make sure we know how to use our calculator. Now is a situation where we need to make sure that we need to know how to use our calculator. All right, what are we going to do first? What? All right, yeah, if you plug it all in, your calculator may or may not make you a happy person. All right, we're going to do PEMDAS. What are we doing first? All right, inside those parentheses, where am I starting? Marcus, where are you going to start? Yep, what are you plugging in first there? Okay, so you got 1 plus 0.036 divided by 2. We know that we have to do 0.036 divided by 2, then add 1. Then what? What comes next? Do I multiply by 5,500? No. What do I do next? I'm going to raise it to the 4th power. And then I'm going to multiply by 5,500. So what is A? What do we get for A, Kennedy?
For A,
82, what comes after?
881.
All right. here's the deal. We should know that money we're going to round to the nearest hundredth. So $5,906.82. Okay, I want to point out to you something that's very particular in this situation. When you are dealing with banks, they don't round the way normal math does. They round to what is to their best advantage. Okay, so let's say that this came out to, I don't know. Let's say we have a situation where the amount of money is $7,246.32, and then there's a 4 and a 9 after it. Okay? Normally we would round this to what? 32 cents, right? We'd round this to 32 cents. Here's the deal. The bank is going to do what works for them. If there is a fraction of money after it, if we're paying on a loan, if we owe them the money, they're going to round this to 33 cents. If they're paying us on a savings account, if they owe us the money, they're going to round this to 32 cents. And if it were like this, okay? In this situation, if I owed them the money, I'd have to pay them 79 cents. If they owed me the money, they would pay me 78 cents. If I owe a bank money, I always have to pay the extra penny. Even if it doesn't round, okay. Now, here's a 0 after the 8.2 that we started with in this situation, so it would just be 82 cents. But if there's a fraction of a penny and I owe them the money, it's an extra penny. If they owe me the extra money, they round down. It doesn't matter if it's a 9 after it. They're going to round this to 78 cents. So in this situation, we are going to round the way a bank rounds. If it's a loan and we're paying, we owe them the extra penny. If it is a savings account and they owe us the money, they're going to not owe us the extra penny. Does that make sense? Questions with that? Okay.